In this video, we're going to be talking about combining vectors mathematically using something that's called the component method. So I'm going to go through the steps in this first slide, and then in the next slide we'll go through a problem. Okay, so step one is to compute the x and y components of each vector organized in a table. Okay, a very important point here is to make sure that you assign a plus sign to an x component that's acting to the right and negative sign to the left, and then for the y components, positive for up and negative for down. And as you'll see again in the next slide, it's easiest to do this whole process by drawing the vectors with their tails at the origin. Okay, so step two then is to compute the algebraic sum of the x and y components. That's simply adding them up, taking into account their signs. And then step three is to plot out the x and y components on the xy coordinate systems. If it's negative, they plot to the left. If it's an x, on the y components, if it's negative, it gets plotted down. Then we use Pythagorean theorem to get the magnitude of the resultant, and right triangle trigonometry to get the direction. Okay, so now we're going to go through a problem that illustrates what we were talking about on the previous slide. We've got a man who walks 5 kilometers north and 8 kilometers 35 degrees west of south and 6 kilometers 45 degrees north of east. We want to find his resultant displacement. Okay, just one word before we start. This process of vector addition applies to any vectors. In this case, it'll be displacement, but it could just as well be force or velocities or any other vector quantity, as you'll see that the more vectors that we study later on in the course. Okay, so I've got the 3 vectors set up here on the xy coordinate system. We have vector A going due north. We have vector B, which is this one here, 8 kilometers 35 degrees west of south. There's south. This angle here would be 35 degrees. That's west, this way being west, of south. And then 6 kilometers 45 degrees north of east. That's vector C here. This angle 45 degrees north of east. Okay, so we're going to find the components using right triangle trigonometry. And you might remember this little acronym, or if you've seen this before, is SOHCAHTOA. This helps you remind the little formulas for computing sine, cosine, and tangent. Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. Tangent equals opposite over adjacent. Okay, so if you don't have that committed to memory, that might help you. All right, so vector A, this one right here, that's the easiest one. Vector A is acting right along the y-axis there, directly north, so therefore it does not have any component along the x-axis. So AX is 0. And its entire magnitude is along the y component. So AY is 5 kilometers, entire magnitude. Okay, we go on to vector B. Vector B is this one down here. We start out with the x component. X component goes right this way. So here's our angle. That is opposite the angle, so we're going to use sine. Sine of 35 is equal to minus bx divided by 8. We're going to solve for bx. Bx is equal to minus 8 times sine of 35, which comes out to be negative 4.6 kilometers. Okay, now we move on to the y component of b. We're going to use cosine for that. Cosine 35 minus by because it's acting downward. By is equal to minus 8 cosine 35, negative 6.6. Okay, finally, vector C, this one right here. This angle here is 45 degrees. Okay, so we start out with the x, which is adjacent to that angle. So cosine 45 equals cx divided by 6. 6 is the magnitude of that vector. So cx is equal to 6 times cosine 45, which is 4.2 kilometers. Okay, then we move on to the y component of c, which would be right here. Okay, that is sine of 45 is equal to cy divided by 6. We solve for cy. 6 times sine 45. This is also 4.2 kilometers because sine of 45 and cosine of 45 are the same value. So here I just transferred the component values into this table. I've got my x components here. Notice I was careful to include the signs here and the y components here. Then down here is just the algebraic sum of these three components, and then this is the algebraic sum of these three components. And down here, this is just summarized. The sum of the x is negative 0.4, the sum of the y is 2.6. Okay, so finally, I created a diagram here. Here's my xy coordinate system. This would be the sum of the x's over here, which was negative 0.4. And then this vector represents the sum of the y's, which was 2.6. Now, to actually do the computation, I would transfer the sum of the x's, that vector, up here so that it's tail to tip with the sum of the y's going like this, and then construct my resultant over here. And then I would compute the magnitude of the resultant by using the Pythagorean theorem. So it would be the square root of negative 0.4 squared plus 2.6 squared. Okay, so if you work through the numbers there, you get a resultant of 2.6 kilometers. And then the last thing to do would be to determine the angle. Since this is a vector quantity, you'd have to know the direction of the angle. So we're going to use right triangle trigonometry. Here is the angle that we want to determine. So I'm going to use tangent of theta is going to be equal to the opposite side, which remember is this vector transferred up here. So that's 0.4 kilometers, and I'm not going to use the sign here because I'm going to make it relative to this diagram. So it's 0.4 kilometers divided by the adjacent side, which is the sum of the y's. That's 2.6 kilometers. So I work through that, and I get 0.15 as the result. Then I do an inverse tan to get my angle, and I get 8.7 degrees. So this angle in here is 8.7 degrees. And I need to express that very specifically. I'm going to express it as 8.7 degrees west of north. Okay, so this is north. So it's that many degrees west, right? That's the westerly direction, it's the easterly direction. 8.7 degrees west of north. A couple of other different ways you could express that. You could express it just as an angle of 98.7 degrees, so that's measured from the x-axis rotating around counterclockwise, so that's 90 plus 8.7, 98.7 degrees. Or you could express the angle relative to the x-axis rotated around this way, clockwise, and that's negative 261.3 degrees. Or finally, the other way you could express it is this angle in here, which is 81.3 degrees, and that would be north of east, because that's the easterly direction, so it's that many degrees north of east.